All right, guys, welcome to day 3. We are going to look over the calendar real quick, and it is including the topics of transformations of exponential functions. Okay, let me maximize this just a little bit. And this optional right here is strictly for you guys. Let's say that you don't have the time necessarily to do the warm-ups. That is totally up to you, but I will tell you right now, they are most beneficial because a lot of times we are spiraling in the content that is current into these warm-ups as well, so that you get that SAT and ACT test prep practice in real time. So our hopes are that you do not just see this word optional and elect not to do these. So please make sure that you are in fact doing them if you do in fact have your that available time. Okay, so clicking on this link right here, okay, it will open up the warm-ups here, and they are for day 1, 2, so on and so forth. And the key is also attached. So in all caps, in red, all these keys are also going to be hyperlinked directly to you to where you can access them, and they look like this. So you have all the answers. Some may be typed out like this, some will be handwritten, but nonetheless, the key will be there available to you. Okay, so here we're going to look at the attributes and list the attributes of y is equal to 2 to the power of x. And again, here are the blank copy of notes, and I've already opened those up. So there's blank copies if you guys want to print these off at home. And then also, just like the SAT, ACT warm-ups, you have the key right attached to it, okay? And I've already opened this up as well, and there it is. So you see in color, in description, paragraph notation, so on and so forth, you are able to still access copied or notes that are already copied out and also in key format, okay? So with all this being accessible to you, our hopes are that you still go ahead and watch the videos that pertain to the content. So here you'll see video day 3A is going to match down here video day 3A. And this coming soon just shows that these are how many videos will be available the following days. And we're not going to get too far ahead because we don't want you guys working too far ahead so that you stay current with the current topics. But if there are no underlined and it's not in blue, as far as the font color is concerned, that means that that link is not active yet, that I still need to record those videos for you guys. But as soon as they are recorded the Sunday prior to that week that we're talking about that it pertains to, then I will go ahead and hyperlink those in and they'll become active, similar to the ones that are active already from day 1 and 2, okay? So with that, I just want to do a brief explanation of that so that you knew what the system was as far as those of you who are just now possibly getting back from spring break and you're looking into these, into the calendar and seeing what all is available and what the format is. Okay, so just like this one, video day 3B for this number 4 is going to be down here accessible, and then video day 3C for the 7-2 practice worksheet is going to be down here. Okay, and last but not least, these are your essential questions as far as what are the big concepts and topics that you're thinking of as you're doing day 3 transformations of exponential functions. And then online with Pearson, 7-2, or the due dates, and so on and so forth, as far as the numbers that you're going to be responsible for as well. Okay. Yes, these due dates are somewhat fluid, but since we've kind of reallocated the workload, treat these as hard due dates, okay, because it is not that much work, and you are definitely able to do it in the time that you have as far as a full week. So these 2 blocks of green, okay, coronavirus green, if you will, day 3 and day 4 is the week of March 23rd to the 29th, okay? Then we'll do 2 days, and you notice that these are in white. These 2 days will be the week of, March 30th through the 5th, and then so on and so forth. We'll just continue as long as we are out of the building, okay? We'll continue at this ongoing updated calendar, okay? All right, so let's go ahead and begin. We're going to start with day 3A, okay? And we're going to go to y is equal to 2 to the power of x. Okay, so here are our notes. So what I'm going to do right now is I'm going to share my iPad so that I can go ahead and annotate. And again, this is my calculator that I can toggle back and forth through all of these things. Okay, so just so that I have it up, I'm going to go ahead and just go back to the calendar, and away we go. All right, so let's go ahead and start off by looking at exponential parent functions, okay? So we're going to start with y is equal to 2 to the power of x. So I'm going to go ahead and put it as f of x is equal to 2 to the power of x. And this is another parent function, if you will, okay? So if I were to go over here to my table and I would say, well, when x is 0, that means when the power is 0, what would the y value be? In other words, what would it spit out here as far as an output y value? Okay, so 2 to the power of 0 is in fact 1, because we know any number to the power of 0 is 1 as long as that number is not equal to like 0 or infinity. Okay, so as long as this number, that's the base, is not 0 or infinity, when it's raised to the power of 0, it will always equal 1. Okay, so let's go ahead and keep going with our table. So 2 to the power of 1 is 2. And then 2 to the power of 2 is like 2 squared, which is 2 times 2, which is just 4. Okay, so there's my table that I can now build points off of. Okay, so we can go ahead and go to 0, 1, which is a very, very important point. Okay, then we have 1, 2, and then we have 2, 4. Okay, and this is our parent function that we're building, that as long as we are going positive numbers, it will increase exponentially like this. And in fact, it doubles each jump. Okay, so it doubles each jump. And the biggest reason why is because the base has a power of 2. Okay, so if the base was, or a number 2. So if the base was number 3, that means it would triple each time. If it was 4 raised to the power of x, it would quadruple each jump. And I'm talking about each individual x value jump. So as you go to the right each jump, that's what I'm talking about. Okay. So let's say that it was 3. You know what I mean? Let's say that we had it to the power of 3. Let me move that down just a little bit. And we have x is 3. So 2 to the power of 3 would be 2 times 2 times 2, because there's 3 of them. And this is equal to 8. So then we would have 3 to the power of 8. Ooh, I did that pretty good. It was already there. 3 to the power 3 would become 2 cubed, which equals 8. Now you're probably wondering, what does it do as you go to the left? Well, for right now, we're going to say that it will approach an already existing horizontal asymptote. Okay, let me go ahead and write this in. This is a line. So horizontal asymptote, the P is a little silent. And it's basically a horizontal line that the graph will approach but never touch. Okay, it'll never touch as far as at the ends. So as you go to positive or negative infinity, it will not touch, it will approach this line. So, but will approach this line. Oops. It'll get infinitely closer, but it'll actually never touch. Now the graph in between, it can go through the line, but I'm saying as it goes to infinity, it will start to hug this asymptote, but never touch, and the same like if it was going to the left. Okay, some graphs might look a little bit easier than that, and the fact of they never cross, and they would look something like this. Okay, so my point is, the end behavior is going to approach but never actually touch that horizontal line. Okay, so in this graph, our parent function, 2 to the x, we're going to show that as you go to the left, it too will approach y is equal to 0, okay, which is my horizontal asymptote for the default parent function. Okay, so HA for horizontal asymptote. And if you wanted to draw it out, it would look something like the following. Let me go ahead and draw this in. So it's a horizontal line, and we show it dashed, that the graph will approach but actually never touch. Okay, so now let's look at this graph. Let's look at the red graph and we're going to describe its domain. The domain that you see is all real numbers, okay? So you can just say it like all real numbers, or you can also say it in interval notation, negative infinity to positive infinity, okay? That is all the x values that you would basically end up touching the graph, the red graph that is, of where it actually exists, okay? If I'm looking at range, these are y values, and I'm going to ask myself what y values are actually touching this graph. And we see that it happens just after y equals 0 and up, okay? So it doesn't hit y equals 0, but happens immediately thereafter. So we're going to label that as, let me go over there, it will be y is greater than 0, or 0 to infinity, open on 0 because it's not touching, and then open on infinity because it will never touch infinity, okay? Just a quick reminder, if this was equal to, this would be a bracket. Just a little FYI. All right, so x-intercepts. X-intercepts are when y is equal to 0. That means it never, in this one, it never touches because the horizontal asymptote is y is equal to 0. So we're going to say no x-intercepts. So we'll say none. And y-intercepts are when x is equal to 0, what's the y value? Okay, so if I go to the graph, my y value is going to be 1. So you could do it two different ways. You could say the y-intercept is 1, or you can show it as a point showing that the y value is the same as this, which is the same as the 1 value here, okay? And yes, this 0 here in this point is signifying where it's located as far as on the x-axis, okay? So at 0, 1 as a point, or y is equal to 1 as just a y value for a y-intercept, okay? So we've already mentioned, and I'll do this in blue since we already have it going on in blue, that the horizontal asymptote is in fact y is equal to 0, okay? And then the end behavior. So let me highlight this as I go. So I'm talking about as x is approaching negative infinity. So here we go. Let's jump on the x-axis and let's approach negative infinity. That's to the left. It wants to know what is the y value of the graph? What is the red part of the graph wanting to approach? So this f of x, this f of x is the y value. And we want to know what does it want to approach? Something that it doesn't have to hit, but that it wants to approach, okay? Or you could say that it's approaching, okay? So let me go ahead and do that. So it looks like the y value is approaching 0, like y is equal to 0. And now let me go ahead and do it with shade. So as x is approaching positive infinity, okay? So let me do this like the following. So let me approach positive infinity. So as x approaches positive infinity, or basically goes to the right, let me write that in. This one goes left. As it goes left, going left, y is equal to 0. As it goes right, the y value is equal to infinity because it is just, it's just jumping upward as far as it's going up to infinity. So way up here would go to infinity. Okay, so that's how we read those. So real quick, just a quick one more time highlight. This would approach infinity because it is going upward here. Whereas before, it would approach 0 because that red graph is approaching the x-axis, otherwise known as y is equal to 0. Okay, so if b, okay, so our default parent function that we got this from is of the following form. Let me go ahead and write this down here. We're talking about y is equal to a times b to the power of x. Okay, so a times b to the power of x. Let me do this like that. So if I'm talking about the b value, Okay, and if this b value is bigger than 1, which our original one was 2, way up here, so I'm going to highlight it blue as well. So if b was bigger than 1, which in this case it is, it's a 2, then we know that the graph is going to have growth of some kind. And we can see that as you go to the right, okay, it's growing. But if b is less than, so we'll say as x values go to the right, the y values are going to go up. That's growth, okay? So let me move that over. Let me write that in so that you understand. Y values are going to go up. Otherwise, what we say increase, okay? But if the blue, otherwise the b value is between, not less than 1, but between 0 and 1. So I want you to imagine, if you will, like a number line system. And what I just showed you was here's 0, here's 1. What we just showed to be growth, okay? What we just showed to be growth over here, we're saying whenever it's bigger than 1 and as it goes to the right, okay? But if it's less than 1 and it's in between 0 and 1 without touching, let me see if I can do this better. All right, so we'll make it a little bit smaller. And I'm talking about between 0 and 1, but actually not touching 1 or not touching, there you go, or not touching 0. This is going to be specifically decay. Okay, that means it's decreasing. That means as you go to the right, x values are increasing, the y values will decrease. Okay, so again, these are x values as you go to the right, and the y values, the respective y values are going to go down, otherwise decrease. That is known as decay. Okay, that is right there. All right, so how about if it was equal to 1? Well, if it was equal to 1, it has neither growth nor decay. And the reason why we say it has to be between 0 and 1 is because if it's way over here to the left, something else is going on. There's like a reflection and possibly a stretch or a compression, otherwise growth or decay that's happening. So we don't want you thinking of that as just one change that is happening, one transformation. Let's say that it was -2 or something to that effect. It would be a little bit more involved as far as how you're interpreting that. So let's just look at it this way: as b will be a positive number, and it will be either between 0 and 1, or it will be greater than 1. If it's equal to 0, then everything's 0. Okay, and if it's equal to 1, nothing's growing or decaying. It's just remaining the same. All right, so I really wanted to get in good detail as far as that goes before we keep going into the rest of these notes right here. All right, so we were looking at quadratic and absolute value functions earlier this year. And the order when we did transformations, and you remember seeing something like this, okay, and it could be for a quadratic function, or it could have been for an absolute value function. And when I'm saying that, it would look like this if it was quadratic, or it would look like this if it was an absolute value function. But nonetheless, the order that we've been doing it was BCAD as far as the order matters of how we list the transformations. Okay, so the transformations of how we list those, order did matter. And we used to do BCAD. Well, this one's just a little bit different, just slightly different, because b in this equation is our base. Okay, and this is going to tell us whether it is doubling, tripling, quadrupling, because it's that number here. Okay, that number, like we have 2, meaning it was doubling each time. Well, that's what I'm talking about here. This b is not a transformation. I want you to look at this b right here. Let me highlight it in gray. I want you to think of that b as the default parent function. Okay, so if you had y is equal to 2 to the x, it's doubling every time. That's a parent. y is equal to 3 to the x, that's another parent, okay? And everything else outside, either in the exponents with x, or in front, like here, with an a coefficient, or d that's adding like a vertical shift up or down, all of those are the transformations, okay? So don't think as b as a transformation in this respect. So we're going to take that off, and the order that we're only concerned with is CAD. Okay, so let me go ahead and list that out. CAD is the order for the transformations. Okay, transformations. So with that being said, let's go ahead and look at our first example. We have 2 to the power of x plus 1 plus 2. Okay, so our default, what we're wanting you to immediately interpret as your default parent function, if you will, is the base is b and the power is x. That we know is an exponential function. So I'm interpreting this default parent function as f of x is equal to 2 to the x, just like what we started way up here. Well, because it's plus 1, what I want you to know is anything in the power is horizontal change, okay? So let me go ahead and go with that. Let me write it out first. Anything in the power is horizontal if it's with the x, and if it's with the y, it's vertical, okay? So let me highlight that. Anything up here will be horizontal, but anything down here in front of that base and over here adding will be a vertical. Okay, so that's the way we're looking at it with this particular parent function. Okay, so let me erase this from before just not to confuse you. And let me erase this because this was from quadratics and from absolute value. I'm talking about this order with this function. Okay, so this one right here is plus 1, which we know is a horizontal shift because it's adding, but it's going to be 1 to the right. Okay, so we're going to describe that right here at the very bottom. Let me go ahead and write that in. This is going to be, and I'm talking about this plus 1 right here, is a horizontal shift 1 unit to the left. Because we do opposite. Plus 1 looks like it's going to go to the right, but everything with the x, we are doing the opposite. And if it's y, you follow the rule. Whatever it looks like, you follow the rule. Just a little reminder. All right. So our next one is there's nothing in here in front as far as showing an a coefficient. So we're going to go straight to the plus 2. Okay, so our second transformation is a vertical because it's with the y. It's going to be a shift because it's adding or subtracting. And we're going to follow the rule by saying it's 2 units up. Okay, so those are my 2 transformations. Okay, the base doesn't affect the transformation. Okay, like we said before, this right here is considered to be the default. Therefore, the base number of 2 does not affect the transformation. Okay, so let's go ahead and draw this out. Okay, we can make a quick little table. And if I make a quick little table, I'm just looking at, all right, what if x was 0, 1, or 2? Okay, or you could even have negative numbers as well. And in this case, we actually will have a negative number because we always want to strive to make our power 0. Okay, by default, we want to make our power always equal 0. So if my function that was given to me, my transformation, was x plus 1, and I want to make it 0, well, then just solve for x, and we know that it would start at negative 1. And then you can keep going positive from there. 0, 1, 2, integer incremental jumps, okay? So let's go ahead and see what their y values are. Well, if I put -1 as an input in my transformation function where x belonged, let me go ahead and make some room for that. If I put it right here, then the power would become 2 to the 0. So 2 to the 0 is 1, plus 2 more would equal 3. And then if I put 0 in, so if I took this 0 and I plugged it into right here again for the x, I'd get 0 plus 1 is 1. 2 to the power of 1 is 2, plus another 2 would give me 4. If I put 1 up there, it'd be 2 squared would become 4, plus 2 more would be 6. And then if I put 2, it'd be 2 cubed would become 8, plus 2 more would become 10. So I can go ahead and graph these x, y values, -1, +3. I could do 0, 4. I could do 1, 6. And then the 2, 10 is off the page. Okay, but nonetheless, there's my graph. Okay, so remember, I asked you to interpret the parent function as the base to the power of x. That means the parent function's horizontal asymptote will start at y is equal to 0. And that's what we labeled here and highlighted or showed with this dashed blue line. Okay? But in this case, there's not a 0 that follows. Okay? It's an actual number that's showing +2. So you guessed it, this +2 was in fact our vertical shift 2 units up, that even the horizontal asymptote is going to shift up 4 units. Okay, so let's go ahead and draw that in. We're going to draw, let me do it this way. Okay, and we're going to shift that 2 units up. So there's my dashed line that the graph will approach, but not touch as you go to infinity or -infinity. And sure enough, if I were to graph this, it would look like the following. It would go here and then exponentially start growing. Okay, so there's my horizontal asymptote. Let me go ahead and label that. The horizontal asymptote is y is equal to 2. And it's not horizontal asymptote, just FYI, it's horizontal asymptote with a T as far as how you spell it there at the end. Okay, so right there, it's a T. All right, so there's my graph. That was a transformation. The key point in starting all of this was making my power 0. -1 as an x value made that happen, so my key point is going to be -1, 3. Looking at this red graph, it looks like the domain is all real numbers, or you could put -infinity to +infinity. Okay, however you want to write it. And the range is going to be y is greater than 2 or 2 to infinity, not touching 2 and never touching infinity. Okay, the horizontal asymptote, please do not put 2. You have to put y is equal to 2. Okay, because a number just by itself, you're going to see, especially in this unit, could mean the x value, could mean the y value, it could mean so many different things. We need you to be explicit. Okay, and yes, because this is increasing, it's going up per se as you go to the right, this is going to be growth. Okay, you're always examining as you're going to the right, as you like go to the future, if you will. So this is exponential growth. All right, so now let's go ahead and move to our second transformation over here to the right. And our parent function that we're going to look at this as, so let me make some room here. Let me see if I can do this. So this is from that one. Yeah, so I'm going to make some room over here. And the parent that we're going to see here is, in fact, f of x is equal to 3 to the power, or not 3. The base is 10 to the power of x. This is our parent function interpretation that we're looking at this equation given in part B. Okay, so that's our parent right there. So now we're looking at the transformations C, A, and D, which are C, A, and D in that order. So let's go ahead and work with that -5. So I'm going to go ahead and point to that here. This -5 is a horizontal because it's with the x. It's a shift because it's adding or subtracting, and it's 5 units to the right because we do opposite with the x horizontal transformations, okay? And then we're going to go down to the a value, which is that positive 3, and this is multiplication. So this is vertical because it's not with the x, it's downstairs with the y, and it's going to be a stretch because that 3 is bigger than 1. Okay, there's a lot of spiraling of former content that we need to remember. We're going to say by a factor of 3. Okay, and then last but not least, let's go back over here to this minus 3. This one is going to be a vertical because it's not upstairs with the x, it's downstairs with the y. Shift because it's adding or subtracting, and then it's 3 down. We don't do the opposite here. We actually follow the rule whenever we're doing the y, okay? All right, so what is our key point? Our key point comes from making our power equal to 0 and solving for that x. So let's say x minus 5 is 0, therefore x is 5 would be the x value of this key point. Okay, and yes, if I put 5 into this equation, let me go ahead and highlight that as I go so that you can see it happen. If I put 5 here, where x goes, I have 10 to the power of 0, which is 1, times 3 is 3. Minus 1 would become 0, okay? Which makes sense because we're trying to make our power become that 0. Okay, that is our key point. That's how we identify that, okay? Now, that was only in this particular instance. Like over here, that didn't happen. I want to bring attention and light to that when I plugged in -1 into the original function way up here, let me go ahead and highlight it. I got -1 plus 1 is 0, 2 to the power of 0 is 1, and then when I added the 2 to it, it became 3. So not all the time will it become 0, okay? But over here, as far as what we were interpreting of making it 0, that was the key point that gave us the x value of 5. Just like the same thing here, what would make that 0 would be if x was -1. So please keep that in mind. The y value doesn't have to always be 0 here, as you can see. All right. Let's keep going. So we're going to make a quick little table. All right, and our table is going to start with 5, and then we go 6, 7, 8, just a handful of points. You're going to jump by integers just like before. And we know this yields a 0. And then if I plugged in 6, if I plugged in 7 and 8, it would give me other numbers too. Okay, so there's a good way to get these numbers fast. We got to be very, very knowledgeable of the calculator, this unit for sure. So I'm going to go ahead and use my calculator to fill this table out fairly quickly. So I'm going to plug into the calculator this equation right here, and it's going to be 3 times, parentheses, 10 to the power of x minus 5. Oops. And then on the bottom, it's going to be minus 3. And I'm going to store, so control store, which are those blue letters right there. We're going to store it as f of x. Okay, so if I want to know what's f of 5, which I already know is 0, it spit out the answer. So I'll say f of 6. Okay, what's f of 7? What's f of 8? So on and so forth. It can give me those values fairly quickly. Okay, so let's look at, let me see. Let's look at, I want to make sure that I inputted this correctly. 3 times 10. Yes, because if I did it by hand, 6 minus 5 is 1. 10 to the power 1 is 10. 10 times 3, because I'm doing PEMDAS, would give me 30. Minus 3 would give me 27. Yeah, so over here, we're going to go ahead and write 27. Okay, so now let's try 7. If I plugged in 7 for x, I'd get 7 minus 5 is 2. 10 squared is 100, so it'd be 300 minus 3 would be 297, which is what I got way over here. So we'll say 297. And then over here, we got 2,997. All right, so if I were to plot these points, okay, what I'm going to do is let's plot 5, 0. So 1, 2, 3, 4, 5. And then I'm going to do it at 0. 1, 2, 3, 4, 5. I'm going to do 627, and already you see it's way, way off the chart. Like it's not even registered. It's way, way too high. Okay. A big thing that I want you to identify is our horizontal asymptote was shifted 3 units down. So when it used to be y is equal to 0, it's now changed to y is equal to -3. And I can go ahead and go 1, 2, 3, and I can start drawing my horizontal asymptote, which is the line that it will not touch as you approach infinity or negative infinity. And then I can go ahead and draw the graph, okay? So let's draw the graph of what it would look like. And it looks something like this. And it grows really, really, really fast because it's not doubling, tripling, or quadrupling each jump. It's multiplying by a factor of 10 each jump. So it's growing really, really fast. So let's go ahead, and the steepness of that graph is definitely a lot steeper than before. All right, so the domain. Domain is all real numbers. The range, I'm going to go ahead and do it in both notations. Y is greater than -3 or -3 to infinity. Open on both because you're not touching -3. The horizontal asymptote we said was y is equal to -3. And it is in fact a growth because you see it increasing as you go to the right. All right, so that's it as far as those problems are concerned. A lot in just that first couple of notes for sure, but let us keep going for sure. Let's look at now, because I want to go through the notes that we have on the calendar. Let's go to, let me show you that over here. The calendar is going to be, and I just realized, I apologize. I didn't have it on this screen to show the actual things that I was saying. So I do apologize, but let me go ahead and show you now, just so that you can see and or take a picture if you need. Everything that we discussed from the key point being 5, 0, all the way to the domain, the range. I just noticed the reason why I didn't scroll back is because when I used the calculator to get these values quickly, I forgot to shift my screen back over. But nonetheless, you see the graph. You can kind of match it with your notes and whatnot, and I think you should be good. Okay, so let's go ahead and go to our notes over here and make sure that we have everything for this video intact. We're going to go all the way. Yeah, we still have. So this video is going to be a little bit lengthier compared to the other ones. The other ones will be a lot less. But let's go ahead and keep going to the second page part